Hey everyone, and welcome to the section on backtracking problems. On this lesson, we are going to solve the problem 1. This problem 1 says, write a backtracking program to print all the combinations of zeros and ones such that z, which is the number of zeros, plus u, which is the number of ones, is equal to n for a given natural number n. So the input consists of a natural number n, this is the only input that we have, a natural number, and the output is all the combinations of z zeros and u ones, such that if we sum the number of zeros plus the number of ones, it gives us the total size that we give on the input, right? Now something also important to keep in mind is that we need to print these combinations one per line and also in lexicographical order. In which sense? Well, we first need to print the combinations that start with 0 and then the combinations that start with 1. Let's see one example to understand this problem. So here we have an example, the input is 3, so we have to print all the combinations, right, of zeros and ones, one combination per line, and in lexicographical order. As we can see, on the output we start with 0 because we are following the lexicographical order. 0 comes before 1. So here, how many zeros we have? We have 3 zeros, so the value for z is 3. How many ones we have? We have 0 ones, so the value of u is 0. So as we can see, we satisfy the restriction. Z is 3, u is 0, and if we sum z plus u, we have that this is equal to n, which is 3, right? And you can try with all these combinations, we satisfy that the number of zeros plus the number of ones is equal to n, in our case is 3. In the same way, here on the second combination, the value of z is 2, because we have 2 zeros, and the value of u is 1, since you only have one value for 1. So if we sum 2 plus 1, we get 3. And you can do this for all the combinations, right? So we can also some sort of see how many combinations we will have as a base of the input. If we have an input n, we will have a total number of 2 raised to n total combinations. If we have 3 as an input, we will have 8 combinations. If we have 2 as the input, we will have 4 combinations. If we have 4 as an input, we will have 16 combinations. So given a value n, we will have 2 to the power of n combinations, right? So let's see how we can implement this program using the backtracking technique, right? So we will solve this problem in C++, okay, in the C++ programming language. You can solve it in any imperative language. You can generalize this idea in Java, in Python, or in any other language. Here, what is important is to understand backtracking, right? So in C++, let's include the input and output a library stream. So we can introduce input and we can also have output displayed. And also we are going to work with vectors, so we need to include a vector library, okay? The vector section was a section that was already studied in this course, right? So here, first of all, let's define the backtracking function. Let's define here is going to be a procedure that is a function that will not return anything. Keep in mind that the backtracking functions are functions that do not return anything. They are procedures. And remember the generic algorithm that we studied on the previous lesson. On the previous lesson, on the section on backtracking, we studied the theory behind backtracking, and we also provided a small guideline for the backtracking process. In a backtracking procedure, we have always two arguments. The argument I, which is the position, or basically the number of values that we have on the solution, and then we have the vector, which is the solution, right? So let's define on this backtracking procedure the two arguments. Let's define here the vector. We can first define the position, which is the index, then the vector, or first the vector and then the position. There's no here relevance in the order of the arguments, okay? So we have here v, and then we will define this I value that we will call idx for index. Very well, so the value n is going to be the value of the size of this vector. So here let's define n to be the size of this vector. Now remember, if you have in C++ a vector object, you can access the size of this vector with v dart size. So if the index that we are dealing with, okay, this index that we're dealing with is equal to the size, is equal to n, then what are we going to do? Well, this means that we've chosen already, in our case, if the value n is 3, it means that we already chose 3 elements to be in the solution. So we just need to print this vector. And this is a function that we will program later. It is basically a function that, given a vector, it will print the vector, okay? Each element separated by a blank space. Now otherwise, and this is the base case. Let's comment here, base case. And now here we have the inductive case. Now for this inductive case, we have two options. The first one is that at the given position index, we choose to have a 0 in that position. And the second option is that, okay, in this position index, I will choose to have a 1. And here is where it is very important the order that we assign. So in the statement they say that we must follow the lexicographical order. This means that we first need to have the zeros chosen to be first and then the ones. Okay, so we will start by setting on the solution, which is the vector v, at position index to be a 0. So what we're doing here is adding a 0. So we are adding zeros, okay, at this position here. So here we add a 0. Let's put concretely what we're doing. We add a 0 at position equal to the index, right? At this index, with this position, we will have a 0. Once we have this assignment, what happens? Well, we already chose this position index, so we need to take the next position. So we apply again an invocation to the same procedure, but now instead of having this index, we will have the index plus 1, right? And the same vector v as we have here, okay? Now this plus 1 here is very, very important so that the algorithm works. This means that we already chose the value for the position index, and now we are going to take the position index plus 1, which is the following position, right? Well, this is when we add a 0 at position index, but we can also have the case that we add a 1 at this index here. So we add a 1, we add a 1 at position equal to the index. So in this case, it is the same idea, but now instead of setting this position to be a 0, we set it to be a 1, and we again do the backtracking process. Now, this example that we're doing here for this problem 1 is really the easiest case for backtracking. Okay, I have a value, a natural number of a value n, and I want the list or the sequence of zeros and ones that has size n. Okay, it is going to be the easiest problem that we will solve on the backtracking technique. Later on, we will see more advanced problems. We will have more restrictions and more constraints to satisfy. So we will have also a set of candidates. We will have to apply the pruning and so on. Okay, for now, we are just generating this sequence of zeros and ones that have size equal to n, right? Now, once we have this algorithm, let's also define the print, because this print here we did not define. So this is very easy. This is basically a procedure that, given a vector as argument, let's also pass this vector as a constant. Since we will not modify this vector, we will just do a loop for all the elements equal to 0 and I is less than n, and we will keep incrementing the value of I. So here n is going to be the size of this vector, right? So if we want to print all the elements, we just here print the element in here. Now, if you want to separate those elements by a blank space, imagine that I have this vector, the vector here, 0, 2, 1, 1, 0, 1. Imagine that we have this vector for a given solution where n, as we can see, is 5, okay? What if I want to print this vector separated by spaces, in the sense of I have 0, 1, 1, 0, 1? Well, at each time that I print the element, I also have to print what? A blank space. Here I have a blank space, here I have another. When I don't need to print a blank space, well, on the last element, right? Because here when I print this last element, we don't have another element to have a blank space. So if you print a blank space at the end, it will be wrong, okay? For presentation, this will be wrong. So to do this, let's just print after each time that I print here the element. If the element is not the last one, so if I is not n minus 1, right? If I'm not dealing with the last one, I will print a blank space. Now keep in mind that the last element in a vector is always the element with index n minus 1, where n is the size of the vector. Right here also we have here a semicolon, like so. So with this we have the print method, okay, that given a vector v, prints the element separated by a space, right? Very well. So we have already the backtracking, okay, algorithm. So now let's just define the main procedure for this problem, okay? So what is the input? Well, the input on this problem is a natural number n. So here let's define a variable for storing this natural number. We will read this variable from the input, right? The user or the client will introduce the input, and then what will we do? Well, we need to apply the backtracking algorithm. So here we just apply backtrack, okay? And now remember, this is a vector we will declare just now, but what is the index that we start from? Keep in mind that this index is how many elements we have already chosen to be inside the solution. So initially, we have 0 elements, right? We have 0 elements, and we keep incrementing the number of elements that we've chosen as we keep assigning values, okay? So initially it is 0, and always in backtracking algorithms, the initial position or the initial number of values that you've chosen is 0, right? So here we have a 0. Now this vector v, we can declare it just above. It's going to be a vector of size n, like so, right? And we will apply the backtracking on this vector, starting from position 0, right? So let's verify that this program is working right. We will start by the example that we have on the problem statement, right? So let's run this program. We are using the Visual Studio IDE for C++. To run a program, we just go to debug and start debugging. If you're using another IDE, then you just run your program as normal. So we run it, and as we can see, the program is waiting for us to introduce the input. So let's here introduce the input equal to 3, right? The value n on this example is 3. So when we press the enter key, we shall see this output, which is the combination of all zeros and ones, such that the length of this sequence is 3. And also in lexicographical order, we first start with zeros and then we go to ones. So we press the enter key, and also before testing this program, if we want the output to be completely equal to the output on this statement, we also need to have line breaks at each time that we print a sequence, right? So it is enough to just here on the print method, once we have printed all the sequence, which is here print, we also print a line break. So we also print an end of line. If we do this, when we end to print and we terminate to print the sequence 0, 0, 0, we will also print a line break. So the next time we print the following sequence, which is 0, 0, 1, we will print that in the next line, and so on. So we run again, and you'll see we introduced 3, which is the input, right? And we expect to see exactly the same output. So we press the enter key, and as we can see, we have precisely the same output as the problem statement. We have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So we have them print in lexicographical order. Now, what if the problem statement asked us to say, okay, instead of the lexicographical order in increased order, print them in decreased order. So you first start with ones, right? The first thing that we should see is the sequence until 0. So what should we change in this case? It is very simple, right? Very easy. Instead of first trying the zeros, instead of first choosing zeros to be part of the solution, we try to choose the ones, right? So we just choose first the ones. So if we first here print this, we are choosing first the ones, we are first assigning ones, and then we are assigning zeros. So let's run this. We can also press F5 to run this program. And now if we print 3, we introduce 3 on the input, we have on the output the same one, but now in decreased order of the lexicographical, right? Because now we are first choosing ones to be part of the solution and then the zeros, right? As we can see, it is very, very simple. We will leave the previous solution, which is the solution to this problem, that we first choose zeros to be part of the solution and then we choose the ones, like so. With this, we finish the resolution to this problem 1. We remind the student that you can download the solution and this code on the downloadable documents of this lesson, as well as the problem statement.